All right, here's 3-2 day 1. And basically what we're doing is we're saying that we've got some points, right? Two variables that we've compared on the scatter plot. And let's say we see a strong linear association. Okay, we talked about that in section 1. Which means we'd see like an R value that's really close to 1 or -1, depending if it's, the association is positive or negative. If that were the case, our calculator will also give us this line of best fit, though I do need to adjust this. We call the y-intercept A and the slope B. If you're looking for this formula on your formula sheet, they use some kind of goofy terminology, B sub 0 and B sub 1. You'll get used to A and B. The hat is very important on the y variable because that means we're talking about a prediction. And in fact, at the end of this lesson, we'll see a case where it becomes pretty important if you're talking about y, which would be an observed y value, or y hat, which is predicted. So, to better dive into this, let's just get a context that kind of fits. I'm not going to make you throw these into your calculator, though if you wanted, you certainly could. The context is, I think, a good one for us because it's pretty intuitive. It's on basically rates of depreciation for, I think it's at Honda CR-Vs from like the 02 to 06 models, and how they've depreciated with miles driven. So it's really clear that you're going to have a negative association. I don't know if it'd be that obvious that it's going to be linear, but it looks like from the data we have that it is. If you were to throw all this into your calculator, you would see an R value of -0.874. I'm okay calling that a strong negative linear association. Okay? In other words, it's a case where the regression line that we would get from the calculator, and remember we get that along with R and R squared, might be a useful thing to look at. That line is on the scatter plot, and you can see that the points pretty closely follow a linear trend, and they're not that far off the line. And here it is. Okay? This slide is like super important because it's one of those things that you're guaranteed you're going to be asked to do this. First of all, the y-intercept is 18,773. Okay? And down here, the slope is -86.18. Right? You're probably fine with that. You've seen lines countless times before and would have no problems with those numbers. It is really important, though, that we can interpret them, okay? Which typically is something we like less, but we really have to do, okay? So your y-intercept always happens when your x variable is 0, so just think of, a predicted price for a car that has 0 miles driven. In other words, our line predicts that I'm okay with calling it that, right? You could go either way. You could say an 02 to 06 CR-V with, 0 miles driven, or you could call it new. But our line predicts a new will cost $18,773. Okay, that kind of makes sense, but you really need to keep in mind it is very, very possible with the y-intercept that it doesn't. Okay, very, very often it doesn't. The slope typically will. Okay. Think of change in y over change in x. I always start with describing x. For each additional, that word additional is really important, 1,000 miles driven. This next part is really important too. Our line predicts. That word should be in there because you saw those points on the scatter plot aren't exactly on the line. They're predictions. They might be off a little bit. Our line predicts a decrease in price of $86.18. Okay, that is a slide you will want to keep coming back to again and again and again because it's a really important one. Okay, those are two things that you don't have to wonder about, like, you know, come test time. Is he going to ask us to interpret the slope or the y-intercept of a regression line? I guarantee you that I will. Alright, some more just stuff we can do with our line. We can use it to make a prediction. We don't have any data about a vehicle with 50,000 miles. That's kind of what you could use it for. This is a prediction, so for my final answer here, I need to call it y hat. Alright, because if I refer to y, that's a cost that comes from the table, and I don't have this piece of data in the table. All I'm trying to show you here is that you use it just like any other line, right? It's a function. I put in a mileage, 50 for 50,000. It gives us back a predicted asking price, in this case $14,464. Okay? Now this gets a little bit funny down here. 250,000 is not in our table, so let's go predict that. And we plug in 250, and we get a very strange answer of negative $2,772. Which is fantastic. I'm going to get a car. It's got a lot of miles, but they're going to pay me to take it? No, this just doesn't make any sense, right? It's an example of extrapolation, right? So you should always pay attention. And this really goes for like any function that's modeling a situation. If it was created based off some data, and you have that data in a table, you really need to stick pretty close to your x values. This is another little topic that can be kind of sneaky, that a problem can kind of, you know, especially a multiple step problem can kind of sucker you into doing it, and all of a sudden you're like, oh yeah, I'll plug in 250 and I'll get that answer, and great, we're good to go. You're like, wait a minute, you got a really weird answer because you were, you know, 170,000 miles or whatever beyond an x value that you should have used. Okay? When you do it, you get answers that are not accurate. Okay? So we don't do it. Oh, another really important topic, and that is what we call a residual. Okay? A residual can be calculated for every single piece of data that we have. Okay, it's a relatively simple calculation. It's the actual piece of data minus the predicted. Okay, so I go and get a piece of data, and I'm going to take this one right here. Okay, 45,000 miles driven. Now the coordinate points there were 45, and then it had an asking price of $14,599. Okay. First things first, right? I need to get it predicted. All right. I need to get y hat, so that would come from just plugging in 45. All right. So here's how a residual works. Is I look at the difference. The actual asking price was $14,599. My line gives me a prediction of 14,894.5. The units here are in dollars, and we get negative 295.9. Okay? That's one part of what you would need to be able to do with a residual. The second part is you should be able to interpret it. Okay? The number's important, and the sign is important. Okay? We have no context to compare it yet, but we got a residual that's actually relatively small. We were predicting the price of a car that's almost $15,000, and we were off by less than 300. That's not too bad. If you look at it on the scatter plot, you'll see that point, right, that I highlighted in blue. It's really close to the line. So you will see this really strong connection that when points are close to the line, they have very small residuals. If they're really far away, I think in day 2, I do another residual that's much, much, much bigger. I think I do this one down here, right here, which is at 70,000 miles. That's going to have a way bigger residual because it's farther off the line. Okay, but we should also talk about which side we were on. Okay, we ended up with what we would call an over prediction. Okay, our regression line predicted the price to be $295.90 higher than what it actually was. Okay, the actual point falls below the regression line, which you can see on the scatter plot. All right, last topic of the day we have here is a little method you can use if you want to get the slope and the y-intercept of a regression line. Your first, at this point, I think your first instinct should be, well, I need the data, and I can put it in list 1 and list 2. I'll go stat calc 8, and we're good. Okay? Let's say a problem doesn't, it's not a deal breaker for us. Notice this is the same context. So here's what this problem tells me, and it's actually enough to get what we need. It gives me a mean for my x values. That was miles driven, 50.5. And it gives me the mean of the price. That's the y variable. So it's almost like it's looking at these two variables separately. Standard deviation of x was 19.3. Standard deviation of y is 1,899. And then it threw in there that r was negative 0.874. Okay? No data, just those measurements. It is enough to get the slope and the y-intercept from that info. Okay? I'll show you how we do it here. The two formulas you would use, one is B, which is R times the ratio of their standard deviations. but you have to calculate first, and then you can get A using B. Okay? Now we know these numbers, so I get negative 0.874 times 1,899. Now if you were to crunch that, you get negative 85.99. That's my slope. And it's like, hey, wait a minute, why the difference? Well, I'm using these numbers, which are probably approximations, to do calculations. The actual slope was 86, let's see, negative 86.18. Just rounding error is all that's going on. I'm off by 17 cents. But then A there's the mean of the y's. Now I'm going to have a little more rounding here because I'm going to use my measurement for B, which again is a little bit off, but that's okay. Number crunch that, and I get 18,767, which is like, I think it was 18,773. So it put me off like, what, $6? You know, we could have added more decimal places and had less rounding error, but the idea here, though, is with these formulas, if you are asked to get a regression line, without the data and just from some select measurements, it can be done, and this is the approach we would take.